Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In this lecture, I am going to discuss the generalized linear discriminant functions. In the previous lecture, we have seen that the linear discriminant function Gx is defined as Gx equal to W transpose X plus W0, and if we expand this expression, then we can write W0 plus W1 X1 plus W2 X2 plus WD XD. Okay, so basically these terms are nothing but the inner product between the weight vector and the input feature vector, where the weight vector is given by this and input feature is given by this. Okay, and here the transpose is used because these vectors are basically the column vectors that we assume. Okay, so these terms we can write in the summation form. So this is the final expression for the linear discriminant function that we have studied. Okay, so this expression is linear in terms of the input feature vector x. Okay, so now we would like to add some higher order terms, like suppose we want to add a second order terms. Okay, so if we add the second order term, then the discriminant function will become quadratic discriminant function. So here we will have the higher term, which is the second order term which is added to this discriminant function. Here we can say that xi into xj is equal to xj into xi. So if it holds, then with no loss of generality, we can say that the weight wij is same as the weight wji. That means it is kind of symmetry. Okay, so when we add this quadratic term, then we will have a more complicated decision boundary, and that decision boundary is called the hyperquadratic boundary or hyperquadratic decision surface. Okay. So let us see what is the discriminant function. So we have Gx equal to W0 plus summation Wi xi I equal to 1 equal to d. So this is the linear term. Then we have the quadratic term. Okay. Okay, and here we assume that xi into xj equal to xj into xi. So that means we can say that wij equal to wji. Okay, so let us assume that d equal to 2. So let us consider this case. Then what will happen? This expression will be W0 plus summation I equal to 1 to 2 Wi xi plus summation I equal to 1 to 2 summation j equal to 1 to 2 Wij xi xj, and we can expand this term. Then we will have W0 plus W1 x1 plus W2 x2, and then the higher terms W11 x1 into x1 plus W12 x1 x2 plus W21 x2 x1 plus w22 x2 x2. Okay, now we can put these two values, okay, in this expression. Then we will have w0 plus w1 x1 plus w2 x2. Okay, so these three terms are basically the linear terms. Then we will have the higher terms, okay, that is the quadratic terms. Then we will have w11 x1 square plus, so here these two terms is 2 times because of symmetry. So w12 x1 x2 plus w22 x2 square. Okay, so this was the linear term, and you can see here these are the extra term when we add the quadratic term in the discriminant function. So how many terms we have? We have 1, 2 and 3 terms. So that's why we conclude that for a quadratic discriminant function we have the additional d into d plus 1 divided by 2 coefficients. So here we have w11, w12 and w22. So these three additional coefficients when d equal to 2. So if we put d equal to 2, then 2 into 3 divided by 2. So we have 3 additional terms. Okay. So when we have the additional terms, then definitely it will produce more complicated separating surface because we have the higher order terms. Okay, and when we put gx equal to 0, then it will give us second degree or hyperquadratic surface. Okay, and if the symmetric matrix, so that is the basically the weight matrix, is non-singular, if this symmetric matrix is non-singular, the linear term in Gx can be eliminated by translating the axes. So we can do some manipulations with this matrix and we can eliminate the linear term by using some translating the axis. Okay. So the basic character of separating surface can be described in terms of scale matrix. So whatever we have seen, so the basic character of this separating surface, when we eliminate the linear terms, then we will have the separating surface, and that can be described in terms of the scaled matrix. Okay. So where this weight vector is denoted by this, and the weight vector is symmetric and non-singular matrix. So from this expression, from this final result, we can have some conclusion regarding the separating surface. That means what type of separating surfaces we will have when we will choose these weight matrices. So we will have the type of quadratic separating surface, and that arise in general multivariate Gaussian case. So this is for the Gaussian case. Okay. So if scaled matrix, scaled weight matrix is positive multiple of identity matrix, means positive multiple of the identity matrix is this, that means the scaled weight matrix equal to k into identity matrix, then in this case the separating surface will be hypersphere. Okay. Next, if the scaled weight matrix is positive definite, then the separating hyper surface will be hyperellipsoid, where the axes are in the direction of the eigenvectors of the scaled weight matrix. So, when we will have the positive definite matrix, then the eigenvector of the scale weight matrix will be the axis of the separating surface, and that separating surface is the hyperellipsoid. Okay. And if none of the above two case holds, then some of the eigenvalues may be positive or it may be negative, then in that case the surface is one of the variety, and that is called hyperboloids. Okay. As we keep on adding the higher terms, like the next is the third order, next will be fourth order. So, we can obtain the class of the polynomial discriminant functions, and that can be thought of as the truncated series expansion of some arbitrary discriminant function gx. And in that case, we can write that generalized linear discriminant function as using this expression. Okay. So, here A is basically the d hat dimensional weight vector, and y I x is basically the d hat function of any arbitrary function x. Okay. So, the physical interpretation is that this function, this y I x function maps the point x, that means it maps the feature point x from d dimensional space to d hat dimensional space, and that will be the higher dimensional space. Okay. So, the discriminant function gx equal to A transpose y separates points in the transformed space using a hyperplane passing through the origin. Okay. That means, in the d dimensional space, our decision surface is not linear anymore, which is the function of x. Okay. But when we transform our input feature vector using this function to the d cap dimensional space, then our the feature transformed features will be linearly separable. Okay. And in that transformed space, the hyperplane will pass through the origin, because this is the basically a homogeneous form, because gx equal to A transpose y, it is a homogeneous form, and this homogeneous form means it will pass through the origin. Okay. So, the mapping to higher dimensional space, definitely it will increase the complexity of the learning algorithm. However, certain assumptions can make the problem tractable. Okay. So, we have to make some assumption so that we can handle this type of problems. Okay. Now, some of the advantages and disadvantages of this approach can be clarified by considering a simple example, and here we can consider this example as the quadratic discriminant function given by this expression. Okay. So, the 3-dimensional vector y is given by using this expression. So, here this is a column vector. Okay. So, that means it maps input feature vector x to 3-dimensional feature space using this function. Okay. So, this is the representation of the problem that we have considered. So, here y is our 3-dimensional vector which will transform the 1-dimensional input feature vector to 3-dimensional feature space. Okay. So, that means D hat is basically the 3-dimensional feature space and D is 1-dimensional feature space. Okay. So, here it maps the input feature vector x to y, okay, and the data remain inherently in 1-dimensional space, because varying x causes y to trace out a curve in 3-dimensional space. Okay. That means, whatever the variations is occurring in the 1-dimensional space, it trace in the 3-dimensional space. So, the property of that 1-dimensional feature space is inherited to the 3-dimensional space. Like, if you will observe, this red point is mapped to this red point is mapped to this, and this black point is mapped to this. Okay. And here a linear surface cannot separate the features from the different classes, but when we map to higher dimensional space, then a single that means linear hyperplane can separate the features from the different class, which was not linearly separable in the original feature space. So, if you look at here, this is our A transpose y equal to 0. So, this is our boundary. Okay. So, this boundary divides the y space into two regions, okay, that is R1 and R2. So, this region is also the mapped region, because this R1 hat, which is the mapped region of the R1 region in the original feature space, and R2 hat is the mapped region of original R2 feature space. Okay. So, if we assume that A is -1, 1 and 2, then A transpose y equal to, it will be -1, 1, 2 into 1x square, okay, and we can write -1 plus x plus 2x square, and we can write it is 2x square plus x minus 1. So, this is basically A transpose I, and we can solve this expression, okay, to obtain the solution of x. So, we will have the two solution, okay, one solution will be -1 and other solution will be 0.5. Okay. So, here we have the two solution for this x. Then we can conclude here that the discriminant function g(x) equal to -1 plus x plus 2x square is positive if x is less than -1 or x is greater than 0.5. Okay. So, in that case gx will be positive, otherwise it will be negative. Now, we can map the two-dimensional input space x through the polynomial function f2y. So, in previous case we have seen that we tried to map a one-dimensional input feature space to three-dimensional space. Now, we are trying to map the two-dimensional feature space to the three-dimensional space. So, here we have the input feature vector x1 and x2, and from this a polynomial function y is created, where our input feature vector is the function of these input feature components. So, x1, x2 and some proportionality with the multiplication of these two feature components. Okay. So, here this polynomial function map the two-dimensional input feature vector to three-dimensional feature space, where the features are become linearly separable by using this decision surface, okay, which divides the feature space in two space, that is the R1 hat and other is R2 hat. Okay. So, whatever the points is above this surface, that will be counted to the omega 1, and whatever the points is below to this surface, that will be counted to the class omega 2. Okay. To the end of this lecture, we can conclude that it may be very hard to realize the potential benefit of a generalized linear discriminant function, but we can analyze this as that in case of linear discriminant function, as we had Gx equal to W transpose x plus W0. Okay. So, if we write W transpose x plus x0 W0, where x0 equal to 1, okay, then we can write it as a summation where I equal to 0 to d wi xi, okay, or we can write A transpose y, where we can write A equal to W0, W1, W2, WD transpose, and y is 1, x1, x2 and xd. Okay. So, here A is the augmented weight vector and y is the augmented feature vector. Okay. So, here we can conclude that at least we can get the advantage of generalized linear discriminant function, that we can write the linear discriminant function as in the homogeneous form, so that it will pass through the origin. Okay. If you have any doubt, you can ask in the comment section. Thank you.